Supervised learning techniques in finance. Supervised learning techniques have become foundational in the finance industry, providing tools to make accurate predictions and informed decisions. These methods use labeled data sets where the algorithm is trained to learn the relationship between input and output variables. The key supervised learning models used in finance are linear and logistic regression, decision trees, random forests, and support vector machines, SVMs, each offering unique strengths depending on the type of data and prediction tasks. Linear regression. Linear regression is one of the most commonly used models in finance. It is used to predict continuous outcomes based on one or more predictor variables. In its simplest form, linear regression fits a straight line to a dataset, minimizing the difference between predicted and actual values. The equation for a basic linear regression model is y equals beta 0 plus beta 1x. In this equation, y represents the dependent variable, x is the independent variable, beta 0 is the intercept, and beta 1 is the slope of the line. This method helps analysts understand the relationship between different variables, such as the effect of past stock prices on future price movements. Application in finance. Linear regression is widely used in various financial applications, such as predicting stock prices, assessing risk-return profiles, and performing portfolio management. For instance, by analyzing past stock performance, analysts can forecast future trends. The simplicity and interpretability of this model make it indispensable in financial analysis, allowing analysts to draw quick insights about relationships between financial metrics. Logistic regression.
The traders scan the stocks and survey their portfolios. They're on the lookout for even the slightest opportunity. Their mission?
While linear regression predicts continuous outcomes, logistic regression is designed for binary outcomes, such as yes-no decisions. Instead of producing exact numeric predictions, logistic regression estimates the probability of an event occurring, which can then be mapped to a binary outcome, 0 or 1. The logistic regression model is essential in classification tasks where financial institutions need to assess outcomes like loan defaults or credit risks. The output is a probability between 0 and 1, representing the likelihood of a particular event, such as whether a borrower will default on a loan based on credit history. Application in finance logistic regression is heavily used in credit scoring, where lenders assess the likelihood that a customer will default. It is also useful in binary classifications across other areas of finance, including predicting the success of an investment or the approval of a mortgage application. By generating probabilities, logistic regression helps decision-makers better assess risk. Assumptions and limitations of regression models. Both linear and logistic regression models operate on key assumptions. Linear regression assumes that there is a linear relationship between variables, meaning the change in the dependent variable is proportional to the change in the independent variable. Logistic regression, on the other hand, assumes that the relationship between predictor variables and the log odds of the dependent variable is linear. However, these assumptions don't always hold in real-world financial data, where relationships are often nonlinear and complex. Moreover, both models are prone to overfitting, where they perform well on the training data but fail to generalize to new data. Techniques like ridge and lasso regression are employed to mitigate overfitting by regularizing the coefficients of the regression equation. Decision trees and random forests. Decision trees are a highly interpretable model that resembles a flowchart, where decisions are made at various branches based on the input data. Each decision leads to an outcome, represented by leaf nodes. Decision trees are particularly useful in finance because they are easy to understand and communicate, making them valuable for visualizing the decision-making process. Random forests. One limitation of decision trees is that they tend to overfit the training data, resulting in poor performance on new, unseen data. Random forests solve this problem by combining multiple decision trees into an ensemble. Instead of relying on just one tree, random forests build several trees using random subsets of the data and average their predictions to improve accuracy and reduce overfitting. Support vector machines, SVM. Support vector machines, SVMs, are a powerful supervised learning model designed to find the optimal boundary, or hyperplane, that separates different classes in the data. In finance, SVMs are primarily used for classification tasks, but they can also be adapted for regression problems. SVMs work especially well in high-dimensional spaces, where there are many variables, making them ideal for tasks involving large data sets with complex patterns.
I have drawn it before, but today it has been triggered.
Computation and finance SVMs are used in credit scoring and algorithmic trading, where the model's ability to separate data points into different categories is valuable. For instance, an SVM model can classify whether a particular stock is likely to increase or decrease in value based on past performance and market conditions. SVMs are also used to identify patterns in market data, helping traders develop better strategies in volatile market environments. Neural networks and deep learning in finance. Introduction to neural networks. Neural networks are one of the most advanced machine learning techniques, modeled after the human brain structure. They consist of interconnected nodes, neurons, organized in layers, with each layer performing a series of operations on the input data. The main advantage of neural networks is their ability to learn from data and improve over time, making them highly adaptable for complex financial tasks. Through a process called training, neural networks adjust the weights of the connections between neurons, refining the model's ability to make accurate predictions. This adaptability makes neural networks particularly valuable in finance, where data patterns are often complex and continuously evolving. Deep learning, a more powerful approach. Deep learning takes neural networks to a new level by adding more layers to the network. These deep neural networks can process vast amounts of data, identifying intricate patterns that simpler models would miss. This ability to capture complex relationships makes deep learning especially useful in financial tasks where understanding subtle trends is essential. For example, deep learning models can identify patterns in stock price movements, allowing analysts to predict future market trends with greater precision. By incorporating vast amounts of historical data, these models can capture hidden dependencies that traditional algorithms might overlook. Applications in finance fraud. Detection. One of the most critical applications of deep learning in finance is fraud detection.
I tend to believe that there's a form of cortical cultural recycling, meaning that cultural environments have influenced our brains to recycle old, adaptive, cerebral recourses from past environments to use towards new environments.
Far from being a Homo economicus, the trader is above all a Homo sapien, immersed in a hostile environment, compelled to take risks, and prone to addiction.
Financial institutions use deep learning models to monitor transactions and identify anomalies that may indicate fraudulent activity. Because these models learn continuously from new data, they become more effective at identifying suspicious behavior, even as fraud tactics evolve. Predictive analytics. Deep learning also plays a major role in predictive analytics, where financial analysts use models to predict stock market trends, assess portfolio risks, and forecast currency exchange fluctuations. By capturing nuances in the data that traditional models might miss, deep learning provides highly accurate predictions, allowing analysts to make better informed decisions. Risk management. In risk management, neural networks can predict loan defaults, model economic scenarios, and forecast potential challenges that financial institutions may face. These predictive capabilities enable companies to manage risks more effectively, protecting assets and ensuring stability in volatile markets. Challenges and limitations of neural networks. Despite their power, neural networks and deep learning models come with limitations. First, they require massive amounts of data and computational resources, making them expensive to implement. Additionally, the complexity of these models often leads to what is known as the black box problem, where it becomes difficult to understand how a particular decision was made. This lack of transparency can be problematic in the financial industry, where regulatory compliance and accountability are critical. The future of neural networks in finance. As computing power continues to grow and more financial data becomes available, neural networks and deep learning models will become even more sophisticated. Researchers are also working to address the interpretability of these models, making them more transparent and accessible to financial professionals who may not have a background in machine learning. The future of finance will likely see these tools becoming indispensable, offering unparalleled insights into complex data sets and helping decision-makers navigate an increasingly intricate financial landscape. Conclusion. Supervised learning techniques, neural networks, and deep learning are revolutionizing finance. From predicting stock prices to detecting fraud, these models offer unparalleled insights and decision-making capabilities. As the financial sector continues to evolve, the adoption of machine learning and AI-driven tools will only increase, driving innovation and shaping the future of finance.